Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 8 on squares. Now, I'm not talking about me and all other math teachers, I'm talking about the shape you've been seeing since a young child. So let's launch right into it. Now, the square. The last special parallelogram that we will examine is the square. The humble square is likely one of the first shapes you ever learned the name of, right? You were sitting there in diapers and your parents were opening up books that had pictures and shapes in them and they were going circle, square, triangle, rectangle, right? Even though all rectangles are squares. Anyway, not the point. In fact, all squares are rectangles. In fact, it has more complexity and interesting properties than any of the other types of parallelograms. That's the weird thing. Even though it seems like it's the simplest of them all, it's actually the most complicated of them all. So let's first begin by looking at the definition of a square. A square is a quadrilateral that has 4 congruent sides and 4 right angles. All right, a square is a quadrilateral with 4 congruent sides and 4 right angles. Let's take a look at exercise number 1. Based on the definition above, determine whether every square is also each of the following special types of quadrilaterals. Give a reason for why it is or isn't for a particular type. Okay, so, I want to know, is every square a rectangle? Is every square a rhombus? Is every square a parallelogram? Is every square a trapezoid? If it is, give me a reason why. If it isn't, give me a reason why. All right, pause the video and think about each one of these and then we'll talk about each one of them in turn. All right, is a square a rectangle? Yes. Why? Because it has 4 right angles. So if you ever had a teacher at any point in math give you some problem that had 4 figures and say which one's the rectangle and you picked the square and they counted it wrong, well, that's a shame because every square is also a rectangle and that means every square has every property of a rectangle. Is a square rhombus? Yes, because it has 4 congruent sides. And again, very important, right? It means that every property of a rhombus is a property of a square. Is a square a parallelogram? Yes. And here I could give 2 reasons, but I'm just going to go with the first one because all rectangles are parallelograms. Or I could say all rhombuses are parallelograms. Right, either way, because every square is a rectangle or every square is a rhombus, right? And those 2 are both parallelograms, then every square is a parallelogram, which means every square gets every property that parallelograms have. And finally, is a square a trapezoid? Yes. And that's because all parallelograms are trapezoids. So a square is basically every type of special figure that we've seen so far. And it's got all of their properties as well. Let's get into that. All right, the extensive properties of squares. Let's take a look at exercise number 2. Square ABCD is shown to the right. Besides having 4 congruent sides and 4 right angles, list the properties that ABCD has based on it falling into each of the following categories. All right, well, ABCD is a parallelogram, right? That's true because all squares are parallelograms. So what properties does the square get from the parallelogram? Well, one could argue that the diagonals bisect each other. Now, there are other properties of parallelograms, right? Let's talk about the other properties, right? Besides the fact that the diagonals bisect each other, we also have opposite sides congruent, opposite angles congruent, and we have adjacent angles supplementary. Now, a little tricky, those last three things, the opposite sides being congruent, the opposite angles being congruent, and the adjacent angles being supplementary, one could make the argument that all three of those simply come from the definition of what a square is. All right. In other words, a square has got four right angles, so obviously the opposite angles are congruent and the adjacent angles are supplementary, and also a square has got four congruent sides, so obviously the opposite sides are congruent. All right. The one thing that doesn't just sort of come naturally from the definition of a square, that really just comes from a square being a parallelogram, is the fact that the diagonals bisect each other. But let's list the other three here just so that we can review them. Now, what do we get from the fact that ABCD is also a rectangle? Well, we get everything from above, right, because rectangles are parallelograms, but the big one with rectangles, right, are that the diagonals are congruent, right? And that's the biggest piece that we get from the fact that it's a rectangle. Okay, so in a square, the diagonals are congruent because all squares are rectangles, and in all rectangles, the diagonals are congruent. And finally, what do we get from the fact that ABCD is a rhombus, right? All squares are rhombi or rhombuses, and therefore, what do we get? Well, two major things, both about the diagonals. The diagonals bisect the vertex angles, and the diagonals are perpendicular. Right? And it's very important to understand about a square, right? So like these two diagonals, when drawn in, right, they're perpendicular to each other. As well, right, this angle and this angle would have to be congruent. And you'd even know what the measures of them are, right? They'd have to both be 45 degrees because the angle that they're bisecting is 90 degrees. All right? So there's tons and tons of properties that squares get because they fit into every other category, right? Every other category. Now, squares arise frequently in the real world because of their properties, right? We see them everywhere. If you look around, you'll see squares everywhere. We can solve a variety of problems that involve them. Often the Pythagorean theorem will come into play. So let's take a look at that situation in exercise number 3. Kimmy is designing a square garden whose diagonal is exactly 16 feet long. She would like to place fencing around the perimeter of the garden so that it is just surrounded. The fencing she will use comes in 12-foot long rolls. How many rolls of fencing will she need? And how much fencing will be left over when she is done? Round the leftover fencing to the nearest tenth of a foot. All right, so what I'd like you to do is play around with this problem. Pause the video, draw pictures, draw in diagonals, think about what you have. You're going to need your calculator on this one, I think, okay? And see if you can figure out how many rolls of fencing that Kimmy is going to need and how much fencing will be left over when she completely surrounds the square using this fencing. All right, well, the first part of the modeling that I want to do here is by just drawing a picture, right? So I've got my square. And the only thing I really know about the square is that its diagonal is 16 feet long. Now you might wonder about the other diagonal. Well, since squares are rectangles, the two diagonals have the same length, so I'm just going to draw the one diagonal. We don't need fencing around the diagonal, right? We just need it around the square. Now, it's pretty obvious that what I need to figure out is the perimeter of the square, right? I need to know the perimeter of the square, which forces me to figure out the side length of a square. Right? Maybe I'll call that x. Just use x, 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 and x, right? And I need the perimeter, which is going to be 4 times x. But that also means I have to figure out what x is equal to. Now, squares contain 90-degree angles. So what I know now here is that I've got two right triangles, right, either one of which I can work with, that have a hypotenuse of 16 and have two missing sides. Now, normally when I have two missing sides in a right triangle, I'm kind of out of luck. But because these two sides are the same length, now I'm not out of luck, right? I can use the Pythagorean theorem and say x squared plus x squared is 16 squared. X squared and x squared is 2x squared. 16 squared is 256. I can now divide both sides by 2, and I'll get x squared is equal to 128. That's what x squared is equal to. Now, 128 is not a nice perfect square. It just isn't. So when I take the square root of this, I'm going to get a messy answer. All right, but we can deal with messy answers because we have the calculator. All right, so let me just do the square root of 128 and maybe bring this calculator up a little bit higher so I can get to the enter button. All right, and that tells me that one side length is 11 let's say 314. I'll take it out 3 decimal places. And of course, that's in feet. Okay. Now, I want to take that and I want to multiply it by 4, right? The perimeter is going to be 4x, and the great thing on my calculator is I can just hit times 4. That's true whether you're using a scientific calculator or a more complicated graphing calculator. I'm going to get my perimeter is 45, and I think I'll just take this out 2 decimal places, 45.25 feet. All right, so I need 45.25 feet of fencing to go all the way around the square. Now, what I know is that my fencing comes in 12-foot long rolls. All right. Now, 3 times 12 is 36 feet, so that's not long enough. 4 times 12 is 48 feet, and that is long enough, right? So I'm going to need 4 rolls of fencing. That's one part of this problem. How much fencing is Kimmy going to have to buy? 4 rolls of it. How much fencing is left over? Well, for that, right, my total amount of fencing is 48 feet. I need 45.25 feet. So my leftover is going to be 48 minus 45.25, which is going to be 2.75 feet. And they wanted that rounded to the nearest tenth of a foot. So we're going to have 2.8 feet of fencing left over. All right, and that's it, right? Again, this is just a general modeling problem using a square and seeing a lot of the properties of a square come out. Okay, let's keep moving on. Maybe we'll move our calculator down here, get it out of the way. So now let's talk about proving figures are squares. We can prove that a figure is a square in many different ways, and we're going to talk about those in a little bit, and you're going to explore more of them on the homework. The most straightforward, though, is to show that it's got 4 congruent sides and 4 right angles. I mean, that's what a square is. So the easiest, well, maybe not the easiest, but the most straightforward way of showing that a figure is a square is showing it's got 4 sides that are the same length and 4 right angles. Let's take a look at that in the coordinate plane. Exercise number 4. Quadrilateral ABCD has coordinates of A, -6, 2, B, 2, 8, C, 8, 0, and D, 0, -6. Using coordinate geometry, show that ABCD is a square by proving it has 4 congruent sides and 4 right angles. All right, well, think about this for a moment, right? We're going to get our 4 congruent sides by using the distance formula, right? And we're going to get our 4 right angles by using slopes. And those are going to be kind of completely disassociated from each other, right? In one case, what we're really doing with 4 congruent sides is proving that it's a rhombus. In the other case, with 4 right angles, we're proving it's a rectangle. And when we put those two together, as we'll talk about in the next exercise, we get a square. All right, so we've done stuff like this quite a bit at this point. What I'd like you to do is first pause and show that it's got 4 congruent sides by using the distance formula. Then we'll come back and talk about that, and then we'll talk about the 4 right angles. Take a little moment with those distances. All right, let's do it. So first things first, I'm going to figure out the length of side AB. Here we go, square root of 2 minus negative 6 squared plus 8 minus 2 squared. That looks like a division symbol. It's not supposed to be. All right, that gives me the square root of 8 squared plus 6 squared. So AB is the square root of 64 plus 36, which is the square root of 100, and that's 10. Now I just have to hope that everything else also has a length of 10, otherwise I do not have a square. All right, so BC, its length is going to be 8 minus 2 squared plus 0 minus 8 squared. I know these calculations are going to start to be mind-numbingly the same, but this is just what we're doing. We have 6 squared plus negative 8 squared. So BC is equal to the square root of 36 plus 64, which is the square root of 100, which is equal to 10. Awesome. So far, so good. I'm just going to lose my points here in a little bit. CD has a length of 0 minus 8 squared plus negative 6 minus 0 squared. That's going to be negative 8 squared, which is 64, negative 6 squared, which is 36. Again, gives us the square root of 100, which is 10. And finally, DA, its length is going to be the square root of negative 6 minus 0 squared plus 2 minus negative 6 squared. Negative 6 minus 0 squared is going to be 36. 2 minus negative 6 is 8. 8 squared is 64. And yet again, we get the square root of 100, which is 10. Oh my. Okay, so now we've proven that this figure has 4 congruent sides, and what we've really done is proven that it's a rhombus. All right, that's what we know so far. Okay? Now, we want to prove that it's got 4 right angles, and for that, we need to go with slopes instead of distances. Now, I need to write down these coordinate points again, otherwise I'm going to have to be going up and down to look at them. So I'm just going to put them down here so that I can then calculate some slopes. B is at 2, 8. I'm going to do a little wavy line here, right? That's my distance work. C is at 8, 0. You probably never thought that proving something was a square was going to be this difficult. And D is at 0, negative 6. So now what I'd like you to do is pause the video, take a few moments and calculate the slope of each of the 4 sides, and try to make some kind of statement about perpendicularity and right angles. Pause the video now and see what you can do. All right, I don't think I'm going to need my calculator anymore, so I'm going to get rid of that. Let's do it. First, the slope of AB. M is going to be 8 minus 2 over 2 minus negative 6. That's 6/8, and that's 3/4. All right, BC. The slope is going to be 0 minus 8 over 8 minus 2. That's negative 8 over 6, and that's negative 4/3. All right, let me extend my page a little bit, get myself a little bit of extra room. Now I've got CD. For CD, my slope is going to be negative 6 minus 0 over 0 minus negative 8. That's negative 6 over negative 8. Never forget, a negative divided by a negative is a positive. So a slope of 3/4. And finally, for DA, here my slope is going to be 2 minus negative 6, all divided by negative 6 minus 0. That's 8 divided by negative 6. A positive divided by a negative is a negative, and we get negative 4/3. Now keep in mind, what I'm trying to do is prove that I have 4 right angles, right? So this isn't about these slopes being equal and these slopes being equal. That would be true if I was trying to prove it was a parallelogram. What I want to now say is that AB is perpendicular to BC, BC is perpendicular to CD, CD is perpendicular to DA, and finally DA is perpendicular to AB, right? And why can I say that? I can say all of that because slopes are negative reciprocals. So what do I have now? I now have 4 sides that are the same length, 4 right angles. So I can now say, therefore, ABCD is a square because it contains 4 congruent sides and 4 right angles. All right, a lot of work, right? And that's because what makes a square is complicated, right? 4 sides that are the same length and 4 angles that are right angles. Now, there are many, many ways, many sufficient conditions, right, to prove something's a square. Because of the connections between squares and all the other types of special quadrilaterals, there are many sets of sufficient conditions that will allow you to prove that a figure is a square. All right? Most of these rely on the following fact. Let's take a look at this. Squares are quadrilaterals that are both rectangles and rhombuses at the same time. So literally, if you've ever seen what's known as a Venn diagram, right? A circle and another circle, right? And an overlapping section. If you put all the rectangles in one circle and all the rhombuses in another circle, the figures that would be in the overlap, those would be squares. Because what a square really is a rectangle and a rhombus put together. So let's take a look at exercise number 5, the last of this particular lesson. Let's see what we have. For each of the following sets of conditions, explain why they are sufficient, i.e. enough, to conclude that the figure is a square. Think about what each condition tells you about the figure. All right, so what we want to do in each case is explain why the information that we're given is enough to say that the figure is a square. So let's take a look at letter A. A quadrilateral with 4 sides of equal length and at least 1 right angle. Okay, so now watch out here. Here I've got a quadrilateral with 4 sides of equal length and at least 1 right angle. So let's do this one together, right? If I've got a quadrilateral, right, of 4 sides of equal length, right, a quadrilateral with 4 sides of equal length means it's a rhombus, right? That's exactly what it is. Means it's a rhombus, right? All rhombuses are parallelograms, and any parallelogram with a right angle is a rectangle. All right, so, right, what we got, right, is we got a quadrilateral that's got 4 sides of equal length. Now, if we've got a quadrilateral with 4 sides of equal length, it means it's a rhombus. All rhombuses are parallelograms, so automatically, because we have a rhombus, we have a parallelogram. And any parallelogram with a right angle, and you explored this a little bit on one of the homework sets, right, is by default a rectangle. So as soon as we've got a rhombus that's also a rectangle, we have a square. Let's take a look at letter B. A parallelogram with diagonals of equal length and two adjacent sides of equal length. All right, well, this is great. Now at least we're starting off with a parallelogram, right? We're not starting off with just a random quadrilateral. So let's first take a look at that first piece, a parallelogram with diagonals of equal length, all right? Well, any parallelogram with equal length diagonals is a rectangle. Great. So we've got half of the point there, right? Any parallelogram with two adjacent sides of equal length is a rhombus. And again, you looked at that on the homework, right? So when we did the homework on the rhombus, right? So a rhombus is a parallelogram by default, okay? And if I have a parallelogram with two adjacent sides being the same length, then all four sides must be the same length, and therefore it's a rhombus. So if I know I have a parallelogram with equal length diagonals, I've got a rectangle, and if it's got two adjacent sides of equal length, it's got to be a rhombus. Okay. Let's see if you can think about one of these on your own. Let's take a look at letter C. A parallelogram with perpendicular equal length diagonals. All right, this one I think will be pretty easy, but see if you can write down why this must be a square. All right, well, it's kind of cool, right? They're both right there. A parallelogram with perpendicular diagonals must be a rhombus, and a parallelogram with equal length diagonals must be a rectangle. That's it, right? So a parallelogram, God, such a long word, with perpendicular diagonals must be a rhombus, and a parallelogram with congruent diagonals must be a rectangle. Okay, and I'll just leave the red there. I kind of like it. It spices it up. Okay, let's look at our last one, letter D. A quadrilateral, now we're back to quadrilaterals, whose diagonals are perpendicular bisectors of one another, and it contains at least one right angle. Okay, all right, so now this one's a little bit trickier. I want you to think about this a bit, and then we'll get it all down. All right, well first, let's get it to be a parallelogram, right? If diagonals bisect one another, it's a parallelogram, right? Forget about perpendicular, if diagonals bisect each other, it is a parallelogram. Now, a parallelogram with perpendicular diagonals is a rhombus. And a parallelogram with at least one right angle is a rectangle. Whew, that was a tough one, right? So it's interesting because, we have this idea that the diagonals are perpendicular bisectors, but that really tells you two things, right? The fact that they're bisecting each other first tells you that the quadrilateral is a parallelogram. Once you know it's a parallelogram, the fact that the diagonals are perpendicular goes on to tell you that it's a rhombus. But once we have a parallelogram that has even a single right angle in it, it must be a rectangle. And therefore, this also describes a square. Whew. All right, let's wrap this all up. So it's kind of interesting, right? I mean, you go all the way back to being as young as you can be, and you were looking at pictures of a square, right? And yet a square is so amazingly complex because, right, it combines the properties of both rectangles and rhombuses. And because both rectangles and rhombuses are parallelograms, squares also pick up all the properties of parallelograms as well. And that leads to all sorts of interesting things that go on with squares, including a whole host of different ways to prove that a figure is a square. The most straightforward way in my mind when you're working with coordinate geometry is what we saw. Prove that it's got 4 sides of equal length, prove that it's got 4 90-degree angles or right angles, and you've got yourself a square. All right. But as we saw in that last exercise, there are many, many other conditions that you can use to prove that something's a square. All right, we're going to be looking at squares, rhombuses, rectangles, and all sorts of things in a few more lessons in this unit. For right now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.